and good morning, everyone. It's my great honor to be presenting in our final ISDA session for this year. My name is Tang, and I'm a postdoc from the University of Neuchâtel and University of Basel. Today, I'm happy to share our recently work on the development of a modular data assimilation framework for an integrated surface and subsurface hydrological model, which we called HGS-PDAF. In the next 15 minutes, I've covered the following topics. And first, I will start by discussing why we felt the need to develop such a coupled data assimilation system. And then I've dived into the key features and capabilities, advancements of HGS-PDAF framework. And afterwards, I will show a few simple applications using HGS-PDAF. And finally, I will wrap up with a discussion of what these results mean and outline our future directions. To understand why we want to develop such a data assimilation system for an integrated hydrological model. So first, let's think about the challenges in real-time operational hydrological simulation for both the water quantity and water quality. So these simulations need to be both accurate and in real time, timely. We should consider not only the groundwater, the soil moisture, the surface water themselves, but also we consider them in one framework, consider the interaction between these different bodies, and consider their interaction with the changing climate conditions. And for real-time water management, we also need to consider the agriculture infrastructure, like the drains, the channels, the dams, the weirs. And these are important for operational water management, and especially for stakeholders like the farmers. Our motivation is to build a robust system for operational hydrological simulation. And currently, such kind of system is quite limited. And the highlight of our system is flexible to assimilate different types of observations. And especially, we can simulate the noble gas concentrations in the sludge transport process. And this allows us to develop a more comprehensive understanding of the hydrological system by integrating different data sources. As introduced by the title, HGS-PDAF consists of two robust systems. First one is hydrogeosphere, which is an integrated surface, subsurface hydrological model, and the parallel data assimilation framework PDAF. The hydrogeosphere is a physically based surface, subsurface integrated hydrological model, which can simulate the surface water, like the rivers, channels, and the groundwater, the soil water, and deeper groundwater in one framework. It also considers different vegetation types, like the plant, the crop, and it also considers explicitly considers the agriculture infrastructures like the drains, weirs, pumps, dams, and especially it can also simulate the sludge transport at the noble gas concentrations. And the parallel data assimilation framework PDAF, it provides ensemble-based and variational methods, different data assimilation algorithms, and is fully parallelized. And it can be coupled with any numerical models. It's model independent software. Our aim is to reduce the uncertainties by incorporating the real-time operations into this integrated hydrological model to better support the operational decision making. And this slide shows the workflow of HGS-PDAF. So at each time step, the system begins by running the hydrological model HGS. HGS begins by initializing from the restart files, reading their model state and parameters at a particular time step, which are important for continuing the simulation from where it left off. And then the HGS model evolves forward in time and writes new output files, so writes a new restart files. And afterwards, HGS-PDAF comes in here. The first HGS-PDAF will read the key variables in the restart files and write them into the output net_CDF file marked as the forecast. And then data assimilation is performed. The key variables are updated. This is done by PDAF, and HGS-PDAF will write output files again into the net_CDF files marked as analysis, and then HGS-PDAF will also write the restart files for the model for the HGS and replace the old one. So in this case, one time step is done. Then it will be looped over all the time steps until the end of the simulation period. Okay, and for each observation type, we use an independent observation operator module for reading and handling. And the data simulation output is written into net_CDF file, the output file, which are easy to manage and analyze. And in the current version of HGS-PDAF, we provide, so it allows us to update the state variables like the hydraulic heads, soil moisture, noble gas concentrations. These are the state variables, and also the parameters like the hydraulic conductivity, the porosity. And different types of operations can be assimilated alone or jointly. This includes the piezometric heads, soil moisture, and noble gas concentrations. So next we will use 3D synthetic 3D river aquifer model to test the performance of HGS-PDAF. The model has a rectangular domain of 500 meters by 300 meters by 30 meters, and we place a river on the top layer, which has a domain of 500 meters times 20 meters times 2 meters. In the model, we also include 2 pumping wells to extract water from the aquifer, and these wells can be switched on and off according to our requirement. So in this scenario, we implemented a pumping schedule where the wells were switched on for the first 16 days, and afterwards we switch it off. And then after 50 days, we switch it on again until the end of the simulation period for 30 days. We also implemented heterogeneous hydraulic conductivity fields, parameter fields, to introduce some variability and complexity. And to carry out our data simulation experiment, we place 8 observation points in the model with a virtual hydraulic heads, and the observation area we set is 5 centimeters. Data assimilation method we use in this case is a standard ensemble gamma filter. So the ensemble size we use is 100 simulation period, and a simulation period is 96 days. In this case, we update both the hydraulic heads and the hydraulic conductivities by ENKF. For the inflation, we use inflation factor of 0.1, but only when parameters are updated together with state to prevent ensemble collapse and maintain the diversity. And in this case, no localization is used, which means we assume that ENKF assimilate data without spatial restrictions, and the observation have an impact for the whole model domain. On the left-hand side, we show the error, so the accumulated error. So here the error means the difference between the simulated and observed head. So here we compare the open loop run and the simulation run, and we see the accumulated error increased during the simulation period, and for the open loop run after 96 days, this can be up to 14 meters. And with data assimilation, the errors reduced by about 60%. And we also use this simple example to test the scalability of HGS-PDAF. So we test it by running different ensemble size. So here, the ensemble size equals to the number of processes we use, starting from ensemble size 2 and doubling it up to 100. And we see compare. So this figure is normalized to 2 cores, so to ensemble size 2, and we see for an ensemble size of 100, the running times just increased by about 50%. It's not bad. And the code is first open source, and it's available on both GitHub and Zenodo repository. So for using this code, you can just download the source code and then compile it. While there is also a README file there, and you can follow the instruction there, compile the code, and also test it with the example case what we show. So this synthetic 3D case, which is also included in the package. Okay. Next, I'd like to show another application case. They started to explore whether groundwater recharge can be predicted using real-time data assimilation of soil moisture. And we also aim to explore whether we can predict evaporation as well, so together with the groundwater recharge. And to address these questions, we set up a numerical model which can simulate infiltration, evaporation, and soil moisture. And we use data assimilation by assimilating the soil moisture data from the lysimeters to predict the groundwater recharge and evaporation. And we use a 1D color model, which has a horizontal domain of 1 meter by 1 meter. And vertically, we use 150 layers with 1 centimeter depth per layer. And for the boundary conditions, we use the precipitation data from material space and also irrigation data from the lysimeter station. The potential ET is also considered as a boundary condition, and these data are also from material space. And on the bottom boundary condition, we set it as a free drainage, which means all the water within the model within this column can be freely drained, taken out of the column. And for the parameter fields, there are quite a lot of parameters like the soil properties, so the Frank-Newton parameters to define the retention curve, saturated hydraulic conductivity, porosity, and residual saturation. And we define the vegetation properties. For example, for this column, this lysimeter we use, so it's covered by grass. So the parameters for vegetation and for evapotranspiration tree. It's also related to the vegetation type, in this case, grass. And for data assimilation experiment, we also use the standard in-sample Kalman filter method. And the in-sample size in this case is 128. We have observations at 4 different depths, top 10 centimeter, 30 centimeter, 60, and down to 90 centimeter. And we run it for 1 year with a daily update. We changed the update frequency from 1 day, 5 days, and 20 days. In total, 3 scenarios. And we update the soil moisture as well as hydraulic conductivity. And the lysimeter data Okay, thank you. And the observation data, the lysimeter data is the from the lysimeter located at Ackenhorst in close to Zurich in Switzerland, and the soil covered is sandy loam. So it's covered by permanent and irrigated grass, and there it measures the soil moisture, temperature, suction, and seepage. It provides the daily data. And this slide shows the results compared between the open loop run and assimilation run. And here we show the difference between the simulation and observation for the saturation at 2 different depths. And the dashed line shows observation, and the solid lines represent the simulation. And we see the open loop run is somehow at some during some time period, especially after 200 days. Significantly deviated from the observation, and with data assimilation, then these lines are much closer to the observation. And what we focused is actually the groundwater recharge here, so drainage and evapotranspiration. And these 2 figures show the cumulative values for drainage and ET respectively. And if we compare for the open loop with the update by data assimilation, for example, update per 5 days and 20 days with the cumulative error highly reduced, let's say 50% reduced, especially for drainage and for evapotranspiration. The reduction is a bit smaller, but still we see quite a little bit improvement. Okay, in the end, I will wrap up with a short summary. So we developed a couple data assimilation framework for an integrated hydrological model, and we test the performance of this system using a simplified 3D synthetic model. We also applied it for a real-time data assimilation case study in the lysimeter data. And currently we are still testing it with real-world catchment scale model in Zealand, in Switzerland, where we use also the piezometric heads and the soil moisture, and want to see if this works for, say, catchment scale real-world hydrological model. And in the end, I'd like to acknowledge the EU project, Water Agri, to find my job, and the HPC quota granted by the supercomputers in Forschungszentrum Jülich in Germany. And that's the end of my presentation. Thank you for your attention.
Great. Thank you very much, Chi. Very nice talk. So I don't see any questions in the YoPad. Okay. So no questions. So I think in the interest of times, we will